Hello, I'm Byron Peterson. Thank you for your interest in my poster. Today I'll be talking about estimates of imaging bolometer signal from radiated power and nuclear heating in ITER. First, let me give a little background and motivation. For ITER, the main bolometer diagnostic will be resistive bolometers. So we are proposing an imaging bolometer as a complementary diagnostic to provide some redundancy. 80% of the radiated power from ITER will come from inside the last closed flux surface, with 20% of that coming from the high energy X-rays from the core. So one question is, what thickness of foil is needed, bolometer foil is needed to absorb the high energy X-rays? The imaging bolometers react irrelevant due to robust materials and can easily be made with a thicker foil. And imaging bolometers have been tested on JT60 and currently on K-STAR. There's the only bolometer diagnostic, and it's providing 2D radiation profiles through tomography and also total radiated power measurements. So let me first explain the imaging bolometer concept. So here we have a foil inside of a pinhole camera arrangement where the radiation is coming through the aperture and is absorbed by the foil. Then the heat of that radiation is either diffuses to the frame at the edge of the foil, or it's re-radiated in infrared, which is measured by the infrared camera. So using the infrared camera, which is on this side of the foil, we can measure the temperature profile, the 2D temperature profile of the foil, and then since the foil is blackened with graphite, then we use the heat diffusion equation to solve for the radiated power, which is given here by this term, and we have the black body radiation term and the time derivative term and the 2D Laplacian term, which describe the heat diffusion in the foil. So based on that heat diffusion equation, we derive this equation for the noise equivalent power, the sensitivity of the imaging bolometer, using the propagation of errors. And then we have another equation here, a simple equation for the signal level, assuming a uniformly radiating plasma. And taking the ratio of those, then we can get the signal to noise ratio. So these equations are given in terms of all these different parameters, the foil property parameters, the IR camera parameters, the imaging bolometer parameters, plasma parameters, pinhole camera parameters, and so on. So this is a very flexible equation that can be used to design the imaging bolometer. The noise equivalent power density, S here, is proportional to the thickness of the foil, so that means the sensitivity increases with the thinner foil. But if the foil is too thin, then we miss the high energy photons, high energy X-rays. So that's why we have to determine then what foil thickness is necessary before we can calculate the signal to noise ratio. We can use radiation models, SONCO and SOL-PS, to determine the necessary thickness of the foil, because these models, in addition to having the spatial information of where the radiation is coming from, also have give the information on the energy spectra of the radiation. So you can see from these plots that 20% of the radiation is coming from the edge of the plasma, from the SOL-PS part of the model, whereas the other 80% is coming from the core, with a significant fraction of it coming from the high energy Bremsstrahlung, the X-rays coming from the core. So and then also I've plotted the necessary foil thickness to stop a certain photon energy. And if we combine those two sets of data, then down below here we can plot the radiated power fraction absorbed by a foil of a given thickness. So you can see from that if we have a 16 micron foil, we can stop 95% of the radiated power. But this is just assuming the foil is exposed to all the radiation from the ITER plasma and is not collimated. So we can consider this 16 microns to be a lower estimate on the necessary foil thickness. In the previous slide, I showed an equation used to give a rough estimate of the signal at the imaging bolometer foil, but we can derive a more detailed estimate by using the Sanko and SOL-PS models and developing a synthetic diagnostic. So we calculate the projection matrix based on the plasma grid geometry and the pinhole camera geometry, and then by using that projection matrix and multiplying it by the radiation model data, then we can get a synthetic data and a synthetic image. So you can see the synthetic images here from the core radiation and then from the edge that we have for the imaging bolometer. And this gives us an estimate for the signal level for each bolometer pixel. Next we take a look then at the power spectra for each channel. We can get this from this Sanko and SOL-PS data, and here you can see for some representative channels in the imaging bolometer field of view what the energy spectra look like for the radiated power. We can look at individual channels and what the thickness of the foil would be needed to get a certain radiated power fraction. So we plotted that for all these pixels along the midplane here of the diagnostic. And you can see, and then we use this equation here to calculate the radiated power fraction for each foil, depending on the energy of the photons and the foil thickness, then and the incident angle of each channel on the foil, and that tells us then what the radiated power fraction which is absorbed by each pixel. And I plotted that versus the thickness of the foil, and you can see here that for the inboard channels, then you need a thinner foil, of course, and then for the core channels, which have a lot of radiation, you need a thicker foil. And basically, for the channel with the maximum energy, then we will need a 36 micron foil, platinum foil. So you can consider this to be kind of an upper estimate on the foil thickness that is necessary. So we use that. Then my colleague Nishitani-san did a calculation, MCMP calculation of the heating of the foil by gammas and neutrons, and this describes the model that he used, just a one-sector model. The foil, the IRVB, is modeled as a coaxial cylindrical structure with 9 centimeter diameter foil and 5 radial regions. Then, looking at the results, we have a radiated power density on the foil of 246 watts per square meter, and the noise level calculated from our noise equivalent power equation is around 4 watts per square meter. Then the signal to noise ratio is around 64, which is reasonable. In terms of the neutron and gamma heating, the neutrons have a heating of around 1 watt per square meter, whereas the gammas have a much larger, 2 orders of magnitude larger heating of around 124 to 140 watts per square meter, which is around 56% of the peak signal. So this indicates that we will need a shutter to remove the neutron and gamma, remove the signal from the radiation, and then measure the gamma heating so we can subtract that off. So let me conclude. I'm not going to read all these points. Let me just skip first to the future work. In addition to the bolometer that we've shown, the imaging bolometer we've shown, we'd like to also consider a diverter viewing imaging bolometer in order to improve the spatial resolution. We only need 20 centimeter spatial resolution in the core, but we need 5 centimeter in the diverter. So in order to get that, we'd like to have another imaging bolometer viewing the diverter. We can use a thinner foil because it will avoid most of the high energy photons, X-rays from the core. So we can use a thinner foil and have higher sensitivity and have more channels. Also, we'd like to do a more detailed design, including the periscope optics for better signal-to-noise estimation, and do tomography modeling to determine the necessary foil thickness and the achievable spatial resolution, and then compare it to the resistive bolometers. Thank you for your interest in my poster. Please, if you have any questions, send them to me at this email address. Thank you.